You know, I think this is just really always a fabulous thing anytime I get a chance to speak with Siri. Siri.
Yes, Greg.
Siri, set a timer for 38 minutes.
Roger that. T-minus 38 minutes and counting.
There we go. Okay, so now that we have that, and you know, thank goodness, because I don't know what we'd do without Siri. We're going to pick this up with oil. So we talked about some of the uses of oil having to do with getting heat out of the engine, lubricating the engine. So we've got a couple of things that we need to consider ourselves with as pilots. One has to do with the oil temperature. Before you take off, you want to make sure that your oil temperature is within the green settings that you have in your particular aircraft. That oil temperature, I mean, it can be anywhere from like 115 degrees to like 180 degrees oil. It can be maybe even a little hotter than that, but you want that indicator to be somewhere there in the green before you take off. Another thing that you want to check is the pressure of the oil. So you have an oil temperature and an oil pressure gauge. These two things are pretty important with your airplane. So you want to make sure that your oil temperature is warm enough for you to take off. What would be a consequence of taking off with cold oil? That's correct. It could be kind of gooey and kind of like molasses. Well, that's not gonna heat very well. Excuse me, it's not gonna lubricate very well. It's gonna be kind of hard to move, so that oil needs to be warmer so it flows better, right? So you want the oil to be warm enough for you to take off. Now, what could be a problem with pressure? You could have too little pressure or you could have too much pressure. One of the things that I have noticed in my airplane is that one of the things that I have to watch now is the fact that when my oil is relatively cool in my airplane, and even though that I have an engine heater, so I have a Tannis engine preheater that I keep my airplane, you know, plugged in and keep that oil warm. Starting an aircraft with cold oil can be really, really hard on that engine. It's a great way for you to make metal inside that engine. Another thing is that that oil is just so thick is that it creates a tremendous amount of pressure inside that airplane, and that's hard on the seals, that's hard on everything inside the airplane. Well, that pressure piece is one of the things that I have to watch now in the 206. Partially because of the fact that in essence, I'm circulating 3 gallons of oil as opposed to 1.5 gallons. And the other thing, say 3 gallons of oil in my engine versus 1.5 gallons in the Diamonds. So 6 quarts as opposed to 12 quarts, do the math. Then is that even with that engine, that heater that I have, and that keeps my oil somewhere around 100 degrees, is that it really likes to be warmer, because I'll see that my pressure reading on my oil pressure indicator is just outside on the high side of that green band, and that if I don't allow that engine oil to warm up, that shows that my pressure is a little high, and if I go full power with that thing, then the chances that I'm taking is that I can create you know, an overpressure situation inside that airplane just with the thickness of that oil. So I kind of have to watch that, and my airplane takes a little while to warm up, which is, again, kind of a surprise to me, but anyway, it's just things that I'm learning. So so those are 2 things that you need to watch out for. Now, let's say that you're flying the airplane and all of a sudden you look down and you kind of notice, wow, my oil temperature seems to be a little warmer than normal. What do? Remember the OODA loop. Observe, orient, decide, act. Excuse me. So you want to notice those things and then say, okay, why is this happening? What can I do to fix it? Well, let's just say that I'm climbing out on a nice warm summer day. Well, partially what may be happening, and the reason that my oil temperature may be high, is the fact that I have a high angle of attack. I'm not getting the airflow through my cowling to cool off that engine, and the oil temperature reading is a byproduct of the heat inside that cowling because of my angle of attack. So what do I do? Let's shallow out that angle of attack and try to climb out to create more airflow through that cowling to kind of cool things off. So that could be part of it. You may just adjust it here. Now you're going to monitor that and make sure that that fixed your problem. If it didn't, I'm also looking at my pressure levels. Do I have low pressure? One of the things that you do in pre-flight is you do an oil check. You open up the little hatch on the cowling, you pull out the dipstick, and you take a reading on how much oil that you have in that engine based on these little hash mark indicators that you have on the dipstick. You want to make sure that you have sufficient oil in your airplane for safe operations. In most cases, especially with the Diamond, you flip up that little oil door and there's a sticker, and it'll say, you know, do not operate with less than 4 quarts of oil. And then you may also have one that says, for instrument flight, you must have at least 6 quarts of oil. So you may have an indicator like that that tells you how much oil that you need to look for inside this airplane. Then you also have a situation where, like in a Diamond DA-40, it will say that it has a maximum capacity of 8 quarts. 8 quarts is how many gallons? 2 is the correct answer. 4 quarts to a gallon. 4 quarts to a gallon. So 8 quarts is going to be 2 gallons. It'll say that's the max. But here's another thing that they don't tell you, and that is this. I may have a max capacity reading in there, but at some point here from a practical standpoint, it may be less. If you put 8 quarts of oil in the Diamond in your first hour of operation, that oil, you're going to puke out a quart of oil in that first hour. That engine does not like to have that much oil in it. You'll lose a quart of oil in the first hour of operations. You may lose another half quart of oil in the next 10 hours. And then you may fly 20 hours at 6.5 quarts, and that's just where it likes to stay. You need to learn that on your engine. Each one of them is different. I've noticed that mine will hold 12 quarts. If you put 12 quarts of oil in it, it'll puke out that first quart of oil in an hour. It'll settle to 10.5, and I've been flying that thing right now. I think I've put 12 hours on it at 10.5 quarts, and it has stayed right there. That's where it likes to be. So, as long as it's getting lubrication, as long as it's cooling properly, as long as everything else with the health and well-being of that engine is great, then that 10.5 quarts is kind of where it likes to be. Just like with the Diamond, kind of likes to be in that 6 to 6.5 quart range. So what they'll do with a mechanic that says, okay, I have to put 8 quarts of oil in this airplane after an oil change, here's what they'll do. They'll put 7 quarts of oil in the crankcase. They'll put 1 quart of oil back here in the toolbox. So you have that quart of oil. There's 8 quarts of oil in the airplane. There you go. So keep that in mind as well, is that each engine kind of operates a little bit differently. You're going to learn that engine, how much oil it uses, where it likes to be, what type of oil it likes, because there are several different flavors of oil. Just like with fuel, you'll learn the fuel settings. Where does this airplane like to be? How many gallons per hour does it burn in this particular power setting, at this particular altitude, at this particular temperature? You learn all of that stuff. And it's one of the cool things about flying airplanes is the fact that, you know, it's kind of a thinking man or woman's game. And that's kind of why I like it. Anyway, there we go. So we check that oil temperature periodically, we check the pressure, and that's part of it. So we look at the cooling systems. So engine cooling. Remember we said that oil helps cool that engine. You'll also remember that, does it have a picture of this? It does not. On each cylinder, shoot, I wish I could, okay, here we go. Take a look here at figure 7-17. If you look from this kind of a top-down view here, looking at this airplane engine, you'll notice that on those cylinders, and you'll see 4 of them there, they have these lines on them. So you see these lines? This is metal, and these things are called cooling fins. F-I-N-S. Foxtrot, India, November, Sierra. Fins, like a shark. And what happens is that these cooling fins do a couple of things. First of all, they kind of wick the heat from those cylinders out away from the cylinder itself to these outside edges of these cooling fins. And by having these regularly spaced grooves out here, that air circulates between them. So that air is allowed to go between these cooling fins and actually aid in cooling that engine. So that's part of the system. Remember the air flowing in the front of the cowling and out the back? That's part of it. Some airplanes have cowl flaps where you can open and close the cowl flaps because there are certain instances where you want to keep the engine a little bit warmer, especially on landing, so that you don't shock cool your engine. More on that in a minute. And so we look here at engine cooling. Remember oil? The proper amount of oil can help us cool the engine. Remember how the air flows inside here, flows into the cowling, around through those cooling fins, and kind of out this cowl opening or cowl flap. And remember, these cowl flaps can be open or closed here by the pilot on aircraft that are so equipped. Also, another thing that helps us cool the engine is regulating the amount of fuel going into those cylinders for combustion. Remember, a rich fuel setting will actually be cooler than a lean fuel setting. So if, for whatever reason, that little maneuver that I talked to you about before, where you lowered the nose of the airplane and that didn't seem to cool off things enough, you could consider enriching the mixture of the fuel going into those cylinders. That can also help cool things off if that's appropriate for your particular altitude and performance setting. So just kind of keep that in mind. There it talks about that. It talks about the exhaust system helping get the heat away, helping get some of the byproducts of combustion away there. And if we're leaning the engine properly, it's a pretty clean thing that we're putting back in the atmosphere. Most of that you're going to wind up with some carbon monoxide and water vapor, you know, if everything is working correctly. So that's kind of what we're looking for, so that it doesn't contribute as much as like cars do to the carbon footprint, which is kind of a thing that we're hearing more and more about. Then the starting system. So we have to have a way to start the airplane. So remember that ignition that I showed you there, you know, in small aircraft, single engine airplanes, you have a key over here. Multi-engine airplanes, the only key that you have is for the door of the airplane. Everything else is run on magneto switches that you have over here that actually starts the aircraft. So it doesn't really use a key on multi-engine airplanes. So, but in single engine airplanes, you have a key and you start it kind of like you do a car. But what happens when you throw that key over there? Well, here's sort of what happens. And I'm going to show you this thing here right now. Let's look at 7-20 when we're looking at this. Guys, understand that what you're looking at right here is you're looking at a very simple electrical diagram. It is very simple with pictures and everything. It's very different when you look at an electrical diagram for your airplane that is supplied to you by the manufacturer in your POH or your AFM. So this one is kind of designed to just show you kind of the basics of it. So I just want you to understand that. In your airplane, you have a main battery. That's going to be the biggest battery that you have inside that airplane. You may have one, if not two, additional backup batteries that will allow you to operate your avionics in the event of a total electrical failure inside your airplane, which is a pretty rare event. But that is kind of a thing that we always kind of, you know, want to pay attention to. The primary job of this main battery is to start your airplane. The cold cranking amps that this battery provide is what turns that crankshaft inside that airplane with a big flywheel out front. There's a small starter motor that'll extend this little thing. It kind of looks like R2-D2. It's really cute. And it'll shoot out this little arm with this little aperture on this thing that has these little teeth on it that'll grab this big flywheel, and it'll start turning this flywheel, which again is connected to the crankshaft, which is connected to the connecting rods, which are connected to the pistons, which start moving the valves, which start your engine. That's what this battery is designed to do, is to start that engine. Because if you think about it, there's a lot of stuff going on, a lot of things it's got to swing out there, including that big spinny thingy that you've got on your airplane. So that's its main job. So when you turn on your master switch here, allowing a master switch is the alternator and the battery side. To start your airplane, you only need to switch on the battery side of this. You don't need to turn the alternator on yet. Now, some manufacturers will say to turn both on. They don't necessarily have to. The battery side is the one that you want on so that you have an electrical circuit that is closed, meaning that you have electricity going through that electrical circuit to your battery that will in turn open up this battery contactor solenoid that will engage the starter, which is this little thing right here, that starter. This is that little guy that shoots out over here, and it'll pop out here, connect to that flywheel, and turn that flywheel. And then when you let go of the key, that little thing pops back in and turns off. So that's what this is. So you turn on your battery switch, clear prop, make sure that nobody is in front of your propeller. Have your hand on your mixture because you want that mixture to come up after you've primed your cylinders. We'll talk about that in a second. Turn your ignition on. When the engine begins to fire, you slowly advance your mixture to allow the fuel to go into those cylinders, and then you idle your engine at about 1,000 RPM. But the main job of that main battery is to start that engine. Once that engine is started, again, you let go of the key, it'll go back to the both position. Now then, once you get it started, the very first thing you check is your oil pressure. You want to see the gauge on that oil pressure move so that it indicates the fact that it's showing that you have appropriate oil pressure in that engine. If that oil pressure indicator doesn't move and you've had that airplane on and running for about 10 seconds, take your mixture knob, pull it all the way to off. That'll starve the fuel out of the cylinders. Your engine will shut off. Turn off your key. Talk to a mechanic. Figure out, why do I not have any oil pressure? Did you check the oil level before you tried to do it? In some cases, we've heard stories of pilots that are used to just running out their airplanes and just kick the tires and light the fires. They don't do a good engine pre-flight. And they have failed to notice that, oh, by the way, I have an oil leak in my engine and all of my oil is gone. And so they have no oil pressure. Well, it's not going to take too long running that engine without any oil for that thing to come apart. So keep that in mind. So this is kind of the basics about what it takes to start that engine. Once that engine is started, once you have oil pressure, everything else looks good. Before you turn the avionics on, you'll turn the alternator side on. The alternator is that thing that is connected to a flywheel, again, with the belt normally, on your engine. And the alternator is the thing that actually creates electricity. In some airplanes, you have something called a generator, which generates electricity, or the alternator also creates electricity. That electricity actually flows through this main bus system, powering all of the electronics in your airplane, but there's a little bleed-off portion that goes back to the battery and keeps that battery charged. So you have some flow through that actually comes here into the battery, keeping your battery charged, so that in the event of a power failure, the first thing you're going to do is use the electricity in your battery to keep your electronics on. Then you will go to a backup battery, and then in some cases you may have a backup on top of that. So that's kind of how that works. So again, that's kind of an oversimplification about how all of that stuff goes. Now, Figure 7-21, we talk about normal combustion and explosive combustion. Remember that we want a controlled firing. This is kind of what we're after. If we have something that actually explodes or an uncontrolled firing inside this combustion chamber, that can be bad. That puts a tremendous amount of pressure on those connecting rods. It can result in improper timing of all of those things on the other cylinders. It can stop the movement of that piston inside that cylinder, and you have stuff coming apart inside your engine, and it won't take too long for that cylinder itself to want to depart the engine. I have actually seen that happen, not at the time, but after this airplane landed, where there was a twin-engine airplane that had a piston that actually just blew through the side of the cowling because it had a problem. And this is one of the things that happens. The biggest thing here has to do with the type of fuel that you're using and kind of what it is. So we have something here called detonation. Detonation is that thing where you get kind of that explosive charge inside that combustion versus a controlled firing. The primary culprit of detonation is going to be a lower grade of fuel that you're using versus the one that you're supposed to. The reason we don't hear a lot about that anymore is because there really is only one grade of fuel that is readily available at most airports. That is 100 low lead. That's really the only gas option that most pilots have. Back in the day, back when I was starting out, you had 3, if not 4, different kinds of gases that were available for your airplane for a gas internal combustion engine. You had 80 octane, you had 100 octane, you had 100 low lead, and I want to say that there was even one that was higher. It was like a 110 octane or something. I could be wrong, but I seem to remember 4 different kinds of fuel, and they all have different colors. They all have different colors of additives. One was red, one was blue, one was green, I think it was. We'll look at this. I think there's a picture on this here, but that's just kind of one of the things. So detonation is normally caused by a lower grade of fuel than specified by the manufacturer. Another thing here that could also happen is the fact that you have a real high manifold pressure and a low RPM. That's caused by a high power setting and then a low prop setting where it's really lugging on the engine. And that's just really bad for a lot of different things. And another thing is that you may be operating that aircraft excessively lean. So you've kind of leaned it out too much maybe, and that engine starts knocking, it starts making noise. By adding a little fuel, that should smooth itself out. So you kind of have to think about that. So there's detonation, primarily caused by a lower grade of fuel than you're supposed to be using, which again is just really hard to happen now. But then again, you can think of it as operating too lean or operating it with a high manifold pressure setting and having your prop back to too high of a pitch, not a fine pitch, but a lower pitch, with that. So kind of lugging on the engine. That's detonation. Detonation is more likely to be systemic. What that means is that if you have one cylinder that could be detonating, chances are they all are. Why? Well, if you look at that list of bullet points on this list, it has to do with fuel, it has to do with mixture. That's going into all cylinders. So with that, now you have kind of a systemic issue affecting all of the cylinders inside your airplane engine. That's detonation. There's another one that is actually even worse. It's called pre-ignition. Pre-ignition. Pre-ignition is caused, well, one of the things that can cause pre-ignition is carbon hotspots that are allowed to accumulate in the engine. And the reason that those are allowed to accumulate is because perhaps you have been running it too rich. That combustion that's happening, that controlled firing, is not able to burn all of the components that you're trying to shove in it. So if you have too much fuel going on in there, it may not be able to burn all of that, and it leaves carbon residue inside that cylinder. And over time, that residue begins to accumulate. And where does it accumulate? In the worst spot ever, which is on the tips of those spark plugs. So after that controlled firing, there could be a hot spot left on the tip of that spark plug with some of that carbon. And in that first intake, as that fuel and air start to come in, it could explode before it's supposed to. Now you've got two pistons competing for pressure on that crankshaft. That's where you're going to have stuff blowing off your engine. So pre-ignition is bad. One of the ways to combat pre-ignition is to lean appropriately, making sure that you're keeping your engine happy and that you're not feeding it too much fuel and you're not feeding it too little fuel, just right. Okay, so that's kind of what you're looking at there. FADEC, Full Authority Digital Engine Control, FADEC. This is something that is, when I say it's relatively new to the aircraft world, it's been this thing that's been around for about the last 10 years. And what that does is that you have a computer that basically controls almost everything. It will control the amount of fuel going into your cylinders. It will control the pitch of your propeller in some cases. And so it's all done with computers. Computers will run all of this. One of the things that I think of is the Diamond DA42 and the engine management system of the Diamonds, all done with FADEC, where it sends the messages through an engine control unit, or ECU, and it says, here's where we want the props, here's where we want the fuel, and it kind of runs the show. So that basically it's designed to make it easier on the pilot, but ultimately what that means is that in addition to making it easier on the pilot, the computers probably do it better than most pilots do it anyway. So, you know, it's kind of one of those things where, again, another machine is taking over a human's job. So, FADEC is something that you're going to see in some of your airplanes. I want to say the Cirrus SR-22s have some FADEC going on in there. The more complex aircraft will have FADEC. And so you'll be looking at more and more of those making their way into aircraft, here, around you. You will in your flying careers have an opportunity to fly a FADEC-equipped aircraft. Turbine engines. There's a couple of different types of turbine engines. Turbine is a little different than an internal reciprocating aircraft where they don't have pistons or cylinders. Turbines run a little bit different. Is that you have aircraft that basically compress air and fuel. It sucks in air and shoots it out the back. That's kind of one of the ways that it works. Now, with these turbine engines, some of them will be jet engines, kind of like you see here, or in some cases like the Cessna Mustang. I know someone who has one of those. And like a Pilatus PC-12 that has a turbine engine, but it drives a propeller. So you can have a turboprop, which is a turbine engine with a propeller, or a jet engine, which is a turbojet engine, which is a series of fans. So the turboprop, they talk about that here, but this is kind of how this thing works. So here's the difference between a turbojet and a turboprop aircraft. A lot of it, remember, has to do with compressing air, pulling in a lot of air, adding the fuel, and then creating the expulsion of these hot gases and this nozzle through these systems. So this is a way that they create power, by sucking it in the front and blowing it out the back. With a turboprop aircraft, it kind of does the same thing. The aircraft works on the same principle, where you have the compressor that compresses the air, adding the fuel, and then again shooting it out the back, kind of a thing. But in this case, instead of all of that energy being blown out the back, some of that energy turns a crank in the center of this turboprop or jet engine to actually turn a shaft inside it that ultimately turns the propeller. I say ultimately turns the propeller. You'll see that it doesn't have a direct connection to this, because if it did, this propeller would spin at an unbelievable rate, which just can't happen. So there's a gearbox in here that actually slows this propeller down. And so there's a gearing system in there that keeps that propeller from spinning too fast. So that's kind of what happens there with that turboprop engine. Now you have turbofan engines. And with these turbofan engines is that you'll see here that you can pull air in through the combustion chamber here as well to kind of compress this, but that great big inlet fan right here, what they call a duct fan, is something that they use in what we call kind of a high bypass, meaning that you're getting a lot that's going through this inner core of this engine, turning all of these fans, including this duct fan. But this duct fan itself creates an incredible amount of suction in the front end of this airplane, and then it blows it out on the sides of this engine, in addition to all of these hot gases being blown out the back here as well. A lot of your new GE, a lot of your Honeywell, a lot of your Rolls-Royce engines, Pratt & Whitney makes these as well, are going to a high bypass type of engine configuration because they are quieter, they're so much more efficient that airlines really like this type of engine. And then again, you also have a turbo shaft, which is this other thing which combines, another power system here. So you can read about those. That we have exhaust gas temperatures. These are one of the things that we look at on the engine. What are the exhaust gases that are leaving the engine? We typically, on exhaust gases, we're looking at in the Diamond, I'm just going blank here right now. Cylinder head temperatures, we kind of want those sort of in that 360 to 380 degree range. We want to keep the exhaust gas temperatures somewhere around the 1400 degree mark. And then I have a turbo inlet temperature gauge here as well, and I want to keep that probably no more than about 1575 on mine. So you're managing these temperatures by managing the amount of fuel, by opening and closing the cowlings, by adjusting your phases of flight. That's kind of how you do this. We're not really, in this case, going to take a look here at the N1, N2 indicators here on jet engines, but somewhere down the road you will see these here when you're operating these. I know that that's something that I would assume Joseph is going to be pretty keen on looking at here before too very long with these. Thrust variations, you can look here at the thrust variations. For an object damage or foreign object detection or FOD, this is something that when you're at the airport and you're walking around and you see a rock like out there on the taxiway, pick it up. Pick it up, carry it with you, and when you're done, throw it over the fence, out in the road or someplace like that. Because those rocks can get blown around into other airplanes. They could also potentially get sucked into an engine. I know that the folks at Atlantic, they're trained on FOD, foreign object detection and disposal. So if you see something on that ramp that shouldn't be there, it doesn't take too big of a rock to cause a lot of damage there with aircraft or a piece of an aircraft. If you're walking to an airplane and you see a piece, some kind of a piece of metal or some kind of a mechanical thing, make sure that you pick that up, tell your instructor, tell the folks at Atlantic to say, hey, look, it looks like maybe something fell off an airplane here. And because people want to know that just purely from a safety standpoint. So it's our job as we're walking around the airport to make sure that we kind of pick stuff up. That's part of what we're supposed to be doing. Let me look here to see what else we have. One of the things that I want to show you here is figure 7-28, and we look at airflow, and this is something where they're talking about the distortion of the airflow in some kind of a compressor section here of a turbofan engine here, or a jet engine. If you disrupt this flow here, this compressor is not going to operate properly. And it's just kind of like a lot of negative things can happen by disrupting this flow into these jet engines, which is one of the reasons you have to be so careful in how you operate these airplanes, the type of power settings that you have, not flying these into some of these spooky corners of the performance envelopes. They talk about a flame out here, and again, this is a kind of a thing, is that if you rob this airflow flowing in here, they're going to be blowing that fuel into the backs of these engines, back into this compression section of this thing, and if there's no air into it, that fuel basically drowns out the engine, and then it just quits running, and that could be a problem. Performance comparison, you can look at this. We look at this in our commercial class. Airframe systems, let's look here, hang on. Fuel systems, we'll look at that here now. Remember the three things that are necessary for combustion. What are they? That's right. Air, fuel, and spark. So the fuel's got to come from somewhere. Where do we normally store fuel in an airplane in small, basic, even training kind of airplanes? Where do we put the fuel? In the wings. That's where they go. So you have high wing configuration, you have a low wing configuration. A high wing configuration kind of lends itself to gravity, so gravity can kind of be our friend and kind of have kind of this gravity type of a system that helps the main engine-driven fuel pump get the fuel into the engine. So that's kind of a plus. In low wing aircraft, where you're basically having to pull the fuel up from beneath the engine, then you have kind of a pump system that has to happen. So you always have an engine-driven fuel pump, but then you also have auxiliary pumps or electrically driven fuel pumps. These can be used in place of the engine pump if the engine pump fails, or in addition to the pump. I'm trying to look here and just to see if I have gone over my time. I don't think I have. Oh, nope, there it is. There it is. Yep, the old duck on the wall is telling us that we're done here with this second section. So, let me look at this. Yep, there it is. Yep, timer's done. Now back to this. So, we're going to pick this up here, guys, with the fuel system. And if you look at the fuel system, this is what we're going to go into on Thursday. Then we're going to get into the electrical system. Here's that fuel that I was telling you about here as well. So we're going to pick this up with fuel system. We're going to finish with the electrical system, and then that should get us through Thursday. Okay? So, guys, have a fabulous day, and please make sure that you have read through all of Chapter 7 for Thursday. Okay? Guys, I will talk to you later. Have a fabulous day.